Good afternoon and welcome to the ARPAS-UK CPD session with Clogworks Technologies Limited and RIEGL UK. We're delighted to have James Pearce from Clogworks and Jonathan Robinson from RIEGL joining us. And it should be a really informative session. We're looking at UAV LiDAR session and they're going to explain the fundamentals of performing a professional unmanned aerial LiDAR survey. They're going to explain an awful lot more about the details behind it, but a couple of words about our speakers. James is the Sales and Marketing Officer at Clogworks. He's been actively working with new and existing customers to ensure Clogworks delivers the perfect aerial solution. Before that, he worked in Germany with a drone reseller and also used to have his own drone operator business. He draws on his knowledge of different UAV and LiDAR platforms to highlight different advantages. Jonathan is a product sector management manager at RIEGL UK with 23 years experience in the geospatial industry, which is an enormous amount. He has enjoyed international roles, both as a geomatics professional and within the design and manufacture environment, helping customers understand and use the latest geosurvey technology. Specialising in multi-platform dynamic laser scanning for mass point acquisition, don't try saying that too fast, Jonathan uses his experience to demonstrate the capabilities of RIEGL Ultimate LiDAR on unmanned drones, aircraft, land vehicle and marine vessel. So guys, thank you very much indeed for joining us and for taking this session for us. We are delighted to have you, and I am going to hand over to you now. Okay.
Perfect. Right. So, can everyone see that okay?
Yes.
Perfect. So thank you very much, Eleanor, for the introduction, and thanks for everyone for taking the time to view this webinar today on UAV LiDAR scanning. During today's session, we're going to look at the following areas. So I'll start with a brief introduction to Clogworks technology, then a short introduction to our aircraft, the Dark Matter Hex Gen 2, as it's the drone that will be used in any examples during this webinar. We'll then move on to things to consider when selecting the right UAV for LiDAR operations, covering things like performance and why this is important for flight times, maneuverability, reliability and longevity of the aircraft, redundancy and why this is crucial to ensuring the aircraft can continue to operate safely in the event of some form of failure, and how having a future-proofed aircraft can help improve your return on investment. Then we'll explore the basics on how to plan a surveying mission using one of our controllers.
Good afternoon, everybody, and thank you to Elena for her introductions to Clogworks Technology and for inviting RIEGL to join us on this webinar. From my side, I have quite a few slides to go through to help with the technical content. These will be covering an introduction to RIEGL, key components of a LiDAR system, consideration around the selection of a LiDAR sensor, survey planning, and the primary processing functions. But first, I'm going to pass back to James to go through the drone side from a Clogworks perspective. Thank you.
Thank you, Jonathan. So let's get started with who Clogworks Technologies are and what we do. So we were officially founded in 2014 by Pete and Lawrence Opdam. The company was formed on a vast experience of model aircraft with the aim of building precision-engineered, performing, reliable UAVs with a strong focus on safety and reliability. Since the company's inception in 2014, we've developed a set process for manufacturing our drones and combined that with our team's expertise to create consistently performing aircraft. One of the things that makes us unique as a business is that we can manufacture UAVs to our customers' exact specifications. Over the years, we've integrated a wide variety of payloads and sensors into our drones, from emergency Wi-Fi transmission in disaster zones to offshore delivery solutions. Sales, aftercare, service, maintenance, everything is all kept in-house at our premises in Holmfirth, West Yorkshire. One of the most, if not the most important aspect of our aircraft is the attention to safety. We put as much redundancy into our drones as possible to ensure they fly safely. It's also another reason why we choose to stick with the modular design as well, as it completely removes the chances of failure in the arms using a locking arm or having folding propellers. We're absolutely obsessed with delivering the best product we can and have conducted hundreds, if not thousands of flights on the dark matter platform to develop it into the best platform we can possibly offer to our customers. So with regards to our aircraft, today we're going to be looking at the dark matter HEX Gen 2, as this is the platform that RIEGL UK used with their Minivux 3 LiDAR payload. The HEX was originally released in 2016, with the Gen 2 variant being released earlier last year. And here are the overall specs of the Gen 2 HEX. So when it comes to flight times, we go by real world flight times in real environments. In fact, we test the endurance of our aircraft 400 meters above sea level in all sorts of weather conditions. The HEX Gen 2, when used with a dual battery setup, can deliver a 55-minute flight time or 30 minutes with a 5-kilo payload. This makes it a brilliant option for a wide array of applications, such as heavy lift LiDAR operations. In terms of maximum payload weight, the HEX can carry a 6-kilo payload. This allows the aircraft to carry quite a large payload, fully loaded with batteries, while still coming in under 25 kilos. All of our dark matter aircraft come with strong and reliable data links as standard. This is the standard range is around 5 to 10 kilometers, and we also offer an extended range of around 20 to 30 kilometers. Obviously, there are a lot of factors to take into consideration around the range, but our systems have been successfully used in EV loss operations. Because our aircraft are RG pilot based, they have absolutely no restrictions on takeoff and flight zones. This basically means the responsibility lies with the remote pilot, and geofenced areas can be added in if needed. The hardware ecosystem is built around the Cube Orange autopilot. This enables us to integrate a wide variety of payloads and sensors. Furthermore, our aircraft can run on a closed system. This ensures quick, effective operation every time without having to worry about firmware updates or the system being blocked from receiving further updates after a period of time. All of our aircraft are RTK enabled if precise location data is required. We also offer ADS-B options on our UAVs as well, allowing for our drone to be visible to local air traffic control and aircraft, also allowing the pilot to view air traffic in the immediate vicinity. Most parachutes on the market can be integrated at point of sale or retrofitted to the aircraft if your needs change down the line. And in terms of redundancy, as I've previously mentioned, safety is key on our platforms, and they're packed with redundancy options to ensure safe operations every time. Some of these features include things like 3 temperature-controlled IMUs, 3 barometers, 2 GPS modules, and 2 separate power sources when used in a dual battery configuration. So, in terms of things to consider when using an aircraft for a heavy lift LiDAR-based application, on top of what I've already mentioned in terms of redundancy, performance and redundancy is one of the most major things to consider. So one of the biggest things to look at is thrust redundancy. In a nutshell, this is how much spare thrust the aircraft has available whilst fully laden with batteries and payload in flight. Like anything mechanical, the harder it's worked, the more susceptible it is to failure. When carrying a 4-kilo payload, our HEX is operating at around 50% of total thrust. Not only does this provide a huge cushion in the event of a sudden wind shear or evasive maneuver, but it also significantly reduces the stress on vital components like motors and speed controllers. Other things look like a solid GPS lock, and this is absolutely essential for a safe and optimum operation. Our HEX comes with 2 GPS modules configured in such a way that the autopilot will automatically switch to the other module if one is to fail or start providing questionable data. To fold or not to fold, that's the question that a lot of people ask. A lot of drones are now manufactured with folding arms and propellers as standard. Although this is great for easy transportation and quick assembly time, it's always worth bearing in mind that each folding arm or propeller turns into another moving part that could ultimately become a point of failure in the future. Flight times and hot swapping batteries. It's always worth bearing in mind the flight times of an aircraft, especially with EV loss and BV loss applications on the horizon. Soon, we will be in a position where you'll be able to travel further afield in one flight. So this is going to play a bigger part as the surveying community accepts drones more and more into their workflows. Another thing to consider is if the aircraft has the ability to hot swap batteries. This is something quite well known in the industry these days, but for anyone who doesn't know, hot swapping essentially is a pit stop for the drone. It allows batteries to be switched out one by one whilst keeping the aircraft and payload powered up, allowing for quick mission resumption. Finally, another thing to consider is weather conditions that the drone and payload are capable of flying in. According to the Met Office, I actually Googled this as well, it rains on average for a staggering 156.2 days a year in the UK. A lot of aircraft and component manufacturers state that their products have an IP rating, but it's really worth digging into the detail of this statement. As a manufacturer, we've seen in the past that a lot of aircraft start off with an IP rating. The long and short of it is look for an aircraft that can fly consistently in rain, snow, and less favorable conditions. Another thing to bear in mind is integration and customization. So payloads are becoming more and more advanced as the industry progresses. When looking to invest in an aircraft for your business operations, flexibility and customization are absolutely vital. A key example of this is major manufacturers bringing out payloads that are only compatible with the latest platforms. You could be in a position where you have a perfectly functional aircraft, but are no longer to incorporate the latest payloads or sensors. Without a doubt, mass-produced, off-the-shelf enterprise platforms have many benefits, initial price point being one of them. But in a lot of cases, you have to play by the manufacturer's rulebook, purchasing their own branded payloads or from manufacturers that they work with. We're keen to buck this trend as a manufacturer, and like I say, I like to use the word future-proof, and for good reason. We can integrate virtually any payload and give optimum levels of control. We manufacture the damping plates and all the mounts in-house. We aim to make the process of mounting the payload as simple and as fast as possible, and we can offer a wide range of controlling options, like adding a dedicated payload operator controller. The RIEGL Minivux 3 is a great example of this level of integration. So the payload has been mounted to a specially designed damping plate to significantly reduce vibration. This is simply slid onto the payload rails of the aircraft and locked into position. And just for a little piece of extra mind, we've also created payload locking rail nuts on each side. We've also integrated PWM control to the LiDAR, so this can be controlled from the flight controller. Another level of this integration is that we've built a specialized mounting bracket for the RIEGL GNSS module. Simply click it into place and it's locked in with a quick release mechanism to remove it after use. No unsightly aftermarket brackets or gaffer tape solutions, just simplicity. But say a few years down the line, your needs change as a business, you need a new payload feature or something, we can simply integrate the new payload or feature without you having to purchase an entirely new system. The next things to consider are future-proofing. A lot of manufacturers tend to be churning out new versions of their enterprise aircraft on a fairly regular basis. Furthermore, you tend to find that after a certain period of time, you find out that they're no longer providing support in terms of firmware updates or replacement parts. For some reason, drones tend to go in the opposite direction to other forms of aircraft, which tend to have a long life expectancy. Again, this is something that we're looking to tackle as a manufacturer by giving our aircraft the ability to be future-proofed. So how can this be done? We do this by being able to integrate and retrofit additional items from newer generation autopilots to things like parachutes and beacon lights. The image at the top is actually a 5-year-old customer aircraft that we recently retrofitted with our latest generation hardware ecosystem, allowing our customers to continue using a perfectly functioning airframe whilst being able to have access to the latest features. Also, a lot of things are falling into place now with regards to EVLOS and BVLOS operations. In fact, some of our customers are already using our platforms for EVLOS applications. This will be a great ability to have when it comes to things like corridor mapping and coastline surveying. Again, a good idea for future-proofing is to consider how easily things like beacon lights, long-range controller options, ADS beacon, and compatibility with SATCOM or a 4 or 5G network connection can be integrated and configured, as well as being able to have options such as active obstacle avoidance. So the last thing from me on the Clogworks side is I'm going to take a really quick look at mission planning using our controller. Mission planning software can be a costly minefield, from some software being 30 quid for a lifetime license to others costing thousands of pounds every year. I could do an entire webinar on GCS's costs and benefits alone, but some manufacturers are starting to include mission planning applications with their aircraft, and we're no exception to that. So I've created a really quick walkthrough video just to demonstrate how quickly you can arrive on site and plan the mission. Just a little bit of a note, we have had issues with volume on this, so hopefully you can hear it. Failing that, I'll be able to send it out separately if needed.
So I'm just going to run through a very quick walkthrough on how to plan a mission using Q ground control. Q ground control is the standard GCS that is offered with our dark matter platforms, but you can use other GCSs such as UGCS, Litchi, and Mission Planner if required. When you open the application, you'll notice I'm using the desktop application, and it's exactly the same as the tablet version that's on our controllers. When you open it up, you will be greeted with this interface here. And the first thing you want to do is go onto the plan icon here. And then you're greeted with certain options here. You can create a blank mission, a survey mission, corridor scan, or a structure scan, or you can open or import a previously saved mission. So we will click on survey. And the first thing it'll ask you to do is allocate a takeoff point. So we will put that here. And then follow the instructions, click done. And then we want to set the altitude for the aircraft to climb to after takeoff to 50 meters. And we can add your degree of yaw there if required. Once we're done with that, we then click on the red survey box just below. And here you have options to create a basic survey, circular survey, trace, or you can load a KML file. So we will tap basic. We're now met with a nice big green box and some white intersecting lines. Now the green box is the survey area and the white lines is the flight path of the drone. So let's just adjust this into an area that we're happy with. And you'll see as I do this, the time up here is actually updating in real time and also giving you a telemetry distance as well. So if we were to say an area that size, it should take approximately 6.5 minutes to do and a maximum telemetry distance of 155 meters. Once you have made your survey area on here, you then go over to this side here, and here you can change the altitude, but we're going to stick with 50 meters. And then we can also work out the spacing as well. Jonathan will go into this in a little more detail during the project planning slide later on in the presentation, but the spacing is ultimately determined by the swath width. So we'll leave that as is, and we can also change the angle for a transects too. Next, if we go into here, we can adjust the altitude of the flight. So, for example, it's relative to launch. You can have it above mean sea level, or you can have it calculated above the terrain. So as this updates, you'll see that the orange line now matches the approximate elevation of the ground below. Once you're happy with all of that and happy with all of your options, if you click return to launch, we can then change this to another waypoint or land. So we will click land, and we will put that roughly in the same area as the takeoff location. If there's any big deviation between the landing altitude and the takeoff altitude, it's worth putting it in there. Once we're happy with all of that, the next thing we would do is add a geofence. So what this does by adding a geofence in is this stops the aircraft from leaving this area. And then another thing we would look at is rally points. So in the event of an incursion or an emergency, we can add secondary landing zones. So we'll put one there and one there. So once you're happy with the mission, you've set your geofence and rally points. The next thing to do would be to connect the aircraft and upload the flight plan and simply click fly.
So that covers just some of the things to look for when it comes to the right aircraft selection. I'm now going to hand over to Jonathan, who's going to go through the fundamentals of effective LiDAR scanning. Over to you, Jonathan.
Thank you, James, and hello again, everybody. James has already given us a great insight into dark matter hex, so I'll just recap on the key points in relation to the LiDAR integration. So safety and redundancy. Fundamentally, we do not want to go out and have an insurance claim on the first outing. You should be reassured that RIEGL interact with all the platform providers using our sensors to ensure a safe and reliable integration. Stability and low vibration. If the vibration wrongly interacts with the frequencies of the INS, it can result in waves in the point cloud. The data produced from the hex and the Minivux integration is smooth and accurate, as you'll see as we go through this presentation. Flight duration. Usually we want to complete our surveys within our loss boundaries without landing. Versatility and payload. At the present time, the Minivux is integrated. However, the HEX has the capability to mount both the VUX-1 and the VUX-120. Don't worry about the names, we will cover this as we go through the presentation. Ultimately, we want to go out in the field with mission confidence and get on with the job. And I'm sure you can do that with our systems together. Please allow me to introduce RIEGL. RIEGL is an Austrian innovator and manufacturer of high-performance 3D laser scanning systems. I work for RIEGL UK Limited, which is a fully owned subsidiary of RIEGL. Our UK offices is in the delightful and historic city of York, from where we travel the UK and across to Ireland. Our laser scanning portfolio covers terrestrial scanning for the built environment, airborne systems for wide area mapping from manned aircraft, unmanned laser scanning, which is the primary topic for this presentation, and finally industrial measurement, so for example in the form of permanent monitoring stations. As you can see, there is no dilution of our products away from laser scanning. This is our core industry and our primary focus. So let's get going into the topic area. Again, to give you a quick heads up, I have a few slides included. We won't spend long on each slide, but I have faith the visual format will help with the technical understanding. I first want to ensure we are all familiar with the terminology I will use throughout this presentation. So I just wanted to highlight two terms, LiDAR and laser scanning. LiDAR is light detection and ranging. This is a method to calculate the distance between the laser assembly and an object, typically using the time of flight principle. Time of flight in simple terms clocks the time it takes a pulse of light to travel to a target and back. Then when considered against the speed of light, you can ultimately translate it to a distance. Laser scanning, this uses the LiDAR methodology to measure many distances. Measurements are distributed via a deflector, in our case, typically a mirror, different sorts available throughout our products. The angular deflection direction is recorded and associated to the given distance. When repeated millions of times and it's subject to additional platform motion, i.e. flying, the scene can be considered scanned, therefore laser scanning. RIEGL's core technology focus is to design and produce LiDAR sensors with survey-grade measurement precision derived from full waveform analysis. 4 key engineering points within our strategy is to produce sensors featuring a narrow pulse width, small beam diversion, high pulse repetition rates, you'll hear me call this PRR throughout this presentation, and online waveform processing. I'm assuming the audience is a little more familiar with other aerial survey techniques such as photogrammetry, so maybe it's appropriate for me to introduce why you may consider using LiDAR. LiDAR technology is classed as an active sensor. It emits its own energy and detects the backscatter. This is less subjected to environmental conditions, the obvious example being you can operate in a variety of lighting conditions, including darkness, if you wish. The sensor can interpret and log additional information from the pulses received. We can call these point attributes. These include reflectance, that's to help represent differing surfaces, and deviation, which is a type of quality indicator. With every pulse sent out, the sensor has the potential to receive multiple returns via our waveform analysis techniques. This is commonly known as an advantage to find the ground through vegetation. We will cover reflectance and multiple returns later in the presentation. The final point for now is one against the office-based productivity. As the LiDAR data is essentially a lot of recorded values ready to be fed into a formula for calculation, the computing time taken to calculate the first point cloud is very quick in relative comparison to a passive sensor, where significant image modeling has to take place, for example. To represent a visual difference, here you will see a typical LiDAR example where the ground has easily been defined through the forest, whereas the photogrammetry can only model the upper surfaces. So I'll just take you through our ULS LiDAR portfolio. RIEGL offers a portfolio of equipment to suit a variety of area platforms, including VTOLs, fixed wings, helicopters, and multirotors. We are proud to be an integral payload for UAS suppliers around the world. An example of these is, of course, the Clogworks Technologies Dark Matter HEX, which is the multirotor. I've personally flown this along with our MiniVux sensors. As I've just mentioned, the RIEGL MiniVux is already integrated on the Dark Matter HEX in both a traditional underhung and a top mounting arrangement, so for flying under bridges, for instance. It is also entirely possible to fly our VUX1 and our VUX120 sensors on the HEX following a short integration period. To touch briefly on our sensor portfolio, as you can see, we have a sensor option to suit a variety of application needs and their corresponding aircraft. Our sensors differ broadly on how many points we can fire out, the speed we can distribute those points, and the way we distribute them, and the altitude range capabilities. We also have the sensor at the end, which is a bathymetry sensor. It contains a green laser for water penetration. RIEGL can supply both sensor only or fully integrated systems and software for an end-to-end workflow. This presentation concentrates on the system. So we'll just take a quick look at the components. So what makes up a LiDAR system? Firstly, all-important LiDAR sensor, a choice from the portfolio we've just seen. This is the instrument that's doing the surveying. Then, as important, we have an inertial navigation system known as an INS. This is providing the positional and navigational information for the point to hang off. Sensor and the INS are both mandatory selections within a LiDAR system. Complementary to this, we can add camera source to capture additional context, which can be later added as point attributes in the form of a color identity. Associated enabling equipment includes the shock absorbing plates, the GNSS antenna to aid the INS, and finally the software. RIEGL adopt a modular approach to system build, advising on the right components for each business model. Okay, so now we're going to start getting into technical detail. Here I want to touch on the principle of how we get the points distributed on the ground. All RIEGL sensors are what we refer to as mechanical scanning LiDAR. So we are spinning a mirror by a motor to distribute points. We do this for a variety of reasons relating to the laws of physics. However, for this topic area, we can consider it to be to scatter points to the surface in a manner that is closest to a grid pattern. We want to produce ultimately a uniformly distributed point cloud. This grid is made up of points along a line, which is perpendicular to flight heading, and scan lines, which is along the flight heading. Points along a line is affected by the mirror speed, pulse repetition rate, or PRR, and the flight altitude. The separation of the scan lines is affected by mirror speed and the flight speed. This forms part of your mission planning, which we'll touch on later. Concentrating on the sensors that will fly on the medium-sized UAV are listed in the graphic. You can see how these scan parameters differ between each product. It's important to note that both the MiniVux and the VUX1 are 360-degree plane profilers, so the points are distributed across the full circle, whereas the VUX120 is a 100-degree field of view multi-line scanner, including a nadir, forwards and backwards scan line. It is designed to concentrate more points to the ground, thus offering a much higher density. So let's look at the difference between the multi-line MFB sensor and the 360-degree profiler. All three of the sensors initially distribute the points in a nadir scanning orientation. Looking at the green points on the image, you will see that the points are concentrated to the plan view, so ground or rooftops. To obtain more feature definition, you may fly the scene in both parallels and perpendiculars. If you have a VUX120, however, you also have the forward-looking laser. As you fly, you are now also surveying detail on the building facades highlighted by the blue points. Finally, in contrast, you also have the mirror image of this with a backward-looking scan line, ultimately giving more definition to the point cloud under a single pass. An important question is which sensor to select. I think this image is quite self-explanatory. The VUX 120 is all about high productivity, concentrating all the points to the ground rather than on surveying the sky. Whereas the 360 sensors are offering more versatility at the slight expense of lower scanning parameters. Customers who have applications in utility, forestry, carbon, so corridor or wide area mapping, generally are opting for the VUX 120. Traditional surveyors who use equipment in a variety of applications to complement the standard practices often enjoy the 360-degree flexibility of the VUX 1, so they can fly alongside buildings, for instance. All of our V-line sensors perform online waveform processing. This is our core of what our LiDAR technology is. Over the next few slides, I'm going to touch on the multi-target capability, calibrated reflectance, and the fulfillment of high measurement accuracy. The easiest way to understand multiple returns is if you imagine you shine a powerful torch from above through some vegetation or a tree. That torch light will illuminate a number of branches and leaves that fall within that beam. It will finish its journey at the last surface it can find, usually either the ground or a tree trunk, for instance. Each of the objects it lights up is visible because it is reflecting light back from its surface. This reflected light can be detected and thus becomes a pulse return. The example on the image is showing a cornfield. As the vegetation is quite dense, to get the best possible return to the ground, it's usual to adopt a tighter field of view, so the laser is falling between one or two plants rather than across many of them. Here is a visual example using multiple returns. The colors represent first, single, interior, and last hits. Without the multiple returns, the ground may not have been surveyed in full in this example. To put this into reality, here the left image is showing a site survey which is covered by dense trees and bushes. The image right is showing the resultant ground after classification of the point cloud and therefore removal of the above ground features. The black areas are the watercourses. From the waveform, we can also extract the amplitude or intensity, as it's sometimes called, of a pulse, which when evaluated and subject to a specific calibration principle and equation computation, we can produce a calibrated reflectance. This is irrespective of distance from the scanner. The image left is showing amplitude. This changes with distance. Take a look at the red house at the front. The image right is showing reflectance. The coloring is common across the surface type. This can aid the interpretation and CAD extraction of different materials across a point cloud. This image is demonstrating an example of how additional point attributes can be valuable. Image left is from an RGB camera and will be what you would see using photogrammetry techniques. Image right is highlighting past graffiti which has been painted over and is likely to be presenting a slightly different surface texture. Okay, so the stringent way we analyze the waveform is designed to yield high accuracy and high precision laser ranging performance. This is not to be confused with final point performance or system accuracy. A sensor datasheet is often stating parameters for laser ranging only. You should be aware to consider both accuracy and precision. To talk that through, top left, we have a schematic demonstrating low accuracy. So when the sample is averaged, it will fall away from the actual surface target. And low precision, there is a large spread of points about the mean. Bottom right, which is where RIEGL technology is intended, is the opposite, tight spread of points about surface target. Quick note on the schematic, in real life term, the point positioning would be affected by the system performance. However, for the sake of this explanation, this is assumed to be good, fixed, and common across the diagrams for relative comparison. Sensors, of course, exist across the market to fit in all of these categories. Whilst the laser sensor is doing all of the survey work, we can't actually use that information unless we understand very accurately where it is originated from and what angle the sensor was sat at a given instance. For this, we need the INS. The INS is providing position and pose. It's typically updating at 200 times a second. It is GNSS based, so satellite based. It is tightly coupled, so the angular and velocity measurements work hand in hand with the GNSS fixes for self-checking each other, so to speak. It acts as a central time source receiver and distributes accurate pulse per second and time tag to the other sensors. It is, of course, a significant component in the system. The selection of an INS is very important to reflect the most demanding applications that it would be used for. INS selection needs to consider the highest intended mission height and the project specification. This diagram is an exaggerated case to explain the effects of a typical INS roll error versus the flight altitude. Surveyors typically care most about the Z or the elevation results. When the error is observed at nadir, the effect on Z is minimal. Contrary, when the error is observed at the edge of the field of view, it is magnified. If you then double the flight height using the same sensor performance, the error can become significant. This can be reduced, of course, by selecting a higher grade INS for higher altitude surveying. This is also a balance of the weight and cost, and we shouldn't overlook factors such as a tight, short mechanical baseline and fixing of the INS to the scanner and its calibration. The final major sensor addition to the system is a dedicated camera or cameras. These come in all shapes and sizes, types and qualities. For this presentation, I'm not going into the detail regarding imagery, however, just really to say that RIEGL interfaces with cameras. We use the imagery to add color to the point cloud by extending the point attribute in the form of a color identity. The imagery is also exportable for onward uses. So, moving on to factors and considerations around mission planning. Our intent is to plan our missions in a way to achieve the highest productivity and therefore obtain the best results on our investment. Productivity is a balance of parameters so we can fly higher, faster and longer, but importantly, meeting the project specification. The start of a plan is to set the hard limits given by what I will call your initial capability. Broadly speaking, these will include your permissions, your aircraft, and your LiDAR system and the parameters thereof. The wider your capability potential, for example, if you're using a higher grade equipment, the higher your productivity potential. Answers we need to find really are, how do I use my capability within its limits, and what extra things do I need to consider to perform the survey? So now to look at variables. Your variables are essentially factors you need to understand and implement to use your capability. These will include, but may not limit to, the following: meeting point density and performance specifications, providing survey line overlap for your field of view, usually some 20 to 25% overlap, considering terrain variation. Is a level survey sufficient, or do you need terrain following to keep a uniform point grid? What is the worst surface reflectance you may encounter? If surveying tarmac roads, you may need to specify points to a low reflectivity, such as 10 or 20%. Look at the smallest object side within the survey, maybe cables. The example here is, do you wish to capture the sports netting? What is the weather? What is the visibility? Do you require roofs only or facades also? This can alter your flight plan depending on the type of sensor you have. Ground control points. Do we just need checkpoints, or are we using them as incorporation points? This depends on the survey specifications, of course. GNSS corrections. These need to be available for the flight area. Where are they coming from? Luckily, RIEGL have a program to help with a proportion of the planning activity. This is called reparameter. There are a variety of ways to use this program. However, keeping to a headline descriptive level, we push in our capabilities and our variables. It then sends out the scanner settings, flight parameters, confirms point separations, densities, and ultimately our productivity. You will then use these parameters to set your equipment and design your survey. This then pushes back to what James has shown you earlier with the mission planning on the aircraft side. Now to the point cloud processing. Here I'm going to give you some thoughts of how to achieve a reliable deliverable. This is my last section, so we'll be soon coming to a close. RIEGL's focus is to efficiently deliver a robustly registered and reliable point cloud for a variety of onward uses. So a fair tongue twister, that one. RIEGL adopts a post-processing attitude in our workflows, as this gives us the data and statistics needed to compute the highest achievable accuracies for the point cloud. Up until now, we have talked about the laser ranging performance. Now I'm moving on to look at the performance of the points on the ground, which is a direct result leading from our system performance. This graphic is intended to show a basic visual error stack up from a system, with subsequent error reduction by workflow and software. Ultimately, we desire all our points to be delivered in the optimum acceptable error area, providing survey grade results. On the left side, in the grey box, we have residual system errors. These are the errors that would be presented if the system was surveying from a fixed location. These errors are well known, very small, and quite repeatable. They have been reduced to minimum during factory calibration and build processes. To the right, we have the variable errors, which on the whole are made up by placing the system into motion. The position and navigational errors are the largest errors within a kinematic system. The error magnitude will depend on the quality of the sensors chosen and coupled. To reduce the effects of the positional and navigational errors, RIEGL uses a post-process workflow, which includes error reduction through trajectory processing and rigorous point cloud registration. Before we move on to software processing, here is another error stack, generally representing a generic lower grade LiDAR system, maybe just using RTK positioning, for example. This overall would be classed as a mapping grade system. Please do note, however, these stacks are just indicative representations for aid understanding. Regarding the processing of the trajectory, the first important point to make is that in this LiDAR survey, all the survey points are off the trajectory. Put simply, a poor trajectory initially equals poor point performance and vice versa. If a survey is done in real time only, the trajectory result, what would be obtained there and then? In the example top right, we show the trajectory differing with poor GNSS epochs and then snapping back when the good quality fixes are obtained. Bottom right is the post-process approach RIEGL take. As we have logged all of the data, we can analyze all of the data after the event. We initially process in a forward direction, then because of the post-process principle, we can now recompute the data in a backwards fashion, giving us two results. If we merge those results, then subsequently smooth the computation within statistical bounds, we are generating a final trajectory, which is reduced in error and will be used for onward point cloud computation. After we have computed the point cloud using the refined trajectory, we can analyze the errors between overlapping survey lines. This graphic is showing a min to max error between the survey lines of approximately 4 to 6 centimeters in height. We can reduce this error using the RIEGL registration module called REPrecision. REPrecision is basically using all of the available survey data and the preliminary computed point cloud to understand the initial errors that present themselves within the 6 degrees of freedom. Once understood, the calculation engine creates an optimized trajectory which is then used to compute a final point cloud. In case of the example given, the survey lines are being manipulated by up to plus or minus 2 centimeters on average for height and up to 0.01 degrees in roll, which will also affect the elevation. It is also being moved in plan. However, as this is a field, we care much more about the Z/elevation in this instance. This is the result, quite a marked improvement in height. And that's it for the technical detail. I hope it's been relatively insightful. I've got a few more slides to come. I have added a few more surveys which have been undertaken using the Clogworks HEX and the RIEGL Minivux LiDAR, but also including the Nadir camera setup. So this is an area near the Clogworks testing site, which James showed the mission plan on earlier. This is an example of a Powerline survey. And finally, a series of images from an environmental survey conducted at a meadowed floodplain. And that's it from me. Does anybody have any questions?
So that was fantastic, James and Jonathan. Thank you very much indeed. And we already have a number of questions that have come through. So what I'm going to do is just work our way through these. So the first one from Chris, this is probably more for James, in regards to your drone redundancy, 3 IMUs, extra GPS, etc. How do you decide what is enough? Does this stem from the regulator? And in that case, which one do you focus on, and what info and data did they require for any airworthiness permissions?
That's actually a really good question. I think the easiest way to answer that is there's never enough. So what Peter and Lawrence are really determined to do is create the maximum level of redundancy in our aircraft in terms of what we can offer. As far as I'm aware, it's not guided by anybody. It's just as the dark matter platform has developed over time, we've listened to feedback from customers, and we've also assessed what could become a potential point of failure. So it's ultimately a case of making sure that there's backups, full backups really, for these kind of applications. That being said, yeah, I don't think there's ever enough, but we always push for the best possible thing we can. If that answers your question, great. If you want to know more about what we can do, just drop me an email. I'll be more than happy to go into a little bit more detail, Chris. That's
great, thank you. The second question, does the RIEGL INS system speak to the Clogworks INS to ensure they are basically showing the same PNT info? Is that useful at all?
No, is the short answer. We keep our LiDAR sensor quite separate to the aircraft, so we're not interfering with each other. So the sensor which is on the laser sensor is obviously a very high quality sensor beyond what is needed for the aircraft. The aircraft has its own as you relate to there. But yeah, short answer, no, it doesn't.
Okay, thank you, Chris. Does that answer your question? And if you have any follow-ups to that, do please pop them into the Q&A. And a different Chris, one of the biggest challenges I face is scanning under objects, such as the underside of large span motorway bridges by drone. Any suggestions? Now, James, I heard you mention earlier on that you could put the system on top. Is that right? Do you want you take this on?
Yeah, that's correct. So yeah, the Minivux 3 can actually be configured. It can actually be mounted to the top side of the aircraft. And in terms of there's no sort of drop in performance in what it can do. It's actually been strenuously tested with quite heavy offset payloads as well on the top of the aircraft. Yeah, so we have a solution for that. It's simply a case of it's a very, very similar mounting system just on the upside of the aircraft.
Fantastic. That sounds very
Can I
logical,
just add a little bit more in there? From the RIEGL software perspective, of course, if you're going underneath bridge, you're going to lose your GNSS fixes. So going back to the reprecision which I presented there, it's essentially using planes which you can find on either the ground or man-made objects to pull and push results together. So that shouldn't be a major problem either.
Excellent. That sounds like a really good, sensible solution between hardware and software there. That's great. Thank you. We have a question here from Andres Sequeira. What happens when GNSS corrections are lost? Would RIR process be able to carry out PPK?
Yeah, so it doesn't receive corrections in real time is our system. We are logging data, as I mentioned, just so we can get the best accuracies possible. So we're not reliant on losing any corrections sent to the aircraft or the sensor. We combine the trajectory which is logged in the sensor with perhaps the base station which was local to the site, and we do that in the software. Which relates to the slides I presented on the forwards and backwards processing. So it is essentially doing PPK in that respect.
Great, thank you. Here is another one from Richard. I feel like we're throwing 20 questions at you in many respects. I think you're coping amazingly. Can you integrate with a sensor I am designing, asks Richard. I want to detect and map the location of ground-based beacons.
That I believe it's something we can do. Yes. So what we'd have to do is, of course, there's a lot more technicality to that. But yes, there should be no problems. Any sort of sensor or payload integrations, we have the ability to be able to work it out and make it happen. It's again, it's like my go-to line at the minute. If there's anything further, like if you want to sort of drop me a line, we can go into that in further detail, and I can put it through with the technical guys. That's no problems.
Great. And just to reiterate, that's james@clogworks.com.
I should have done that. Yeah, thank you.
That's okay. That's what I'm here for. Lovely. So next question is, what is the training time from scratch for drone and LiDAR survey, and what is the approximate cost?
Well, I can start with that. So we recommend if you've never flown a drone before, we would recommend sort of 2 hours on a smaller craft. So something like a Mavic Mini or something like that. And then it's a case of once we go through that, we actually do a manufacturer training day, which is included in the price of the aircraft. Where you come down, we go through the theory, construction, deconstruction of the aircraft, and then obviously like a hands-on bit on our flying site where we teach you the basics of operating the aircraft safely. Obviously, depending on the circumstances, depending on where you're wanting to fly, you may have to get further authorizations. We don't do them directly, so it'd be a case of obviously going to a training provider, which again we can help with. We can point people in the right direction if required.
Ditto, funnily enough.
Yes, of course.
We can also help with directing you to insurers and a number of other solutions too, so that's not a problem. We have a question here from David. Roughly what sort of cost are we looking at for a basic Clogworks LiDAR system? What I'm going to say there, David, is that given that this is a CPD session, that you email James and Jonathan for a and ask that question outside of the CPD session, please. So Chris has said, great answers, thank you very much. And Andrea Sequeira has also said, thank you too. Do we have any other questions coming through? I'm just checking off the ones that we've talked about. No more questions then for the time being. Last chances, anyone? And if we are done, I'll give everyone a moment because it takes a moment to type these things. But otherwise, thank you very much, James and Jonathan, for a highly informative session here. Chris Ailes has asked can we get a copy of the slides? Are you okay with that, guys? James and Jonathan, to share?
Absolutely, yeah.
No problems at all, yeah.
Lovely. Yes. So Richard has commented, if you're starting out with drones, buy some cheap ones and crash them first. For forestry purposes, flight height and area covered. David, I'm not quite sure what you mean by your question. Lovely, we'll make sure the copy of the presentation comes out with to those who have registered for the webinar. That's fine, not a problem at all. Lovely. David, do you want to expand on what your question is? For forestry purposes, flight height and area cover, do you mean what they're capable of doing or what height they need to be at?
I think from my perspective, that's really dependent on the type of sensor which is chosen, where the forest is, is it on a hill, is it in the tropics, is it in the UK, etc. So maybe they can drop me a message at the email address given there, and I can interact beyond.
Lovely, that's great. So David, that's jrobinson@riegle.co.uk. Okay, well, thank you very much, James and Jonathan, and thank you very much also to all our participants and attendees as well. Thank you for giving up your time to come and listen and watch and discuss. We've much enjoyed seeing you here and we're very grateful for your time. The ARPAS-UK AGM and annual conference is coming up shortly. There are details on our website about that. You are able to attend virtually as a non-member, but as a member you can also come along in person. We will be at Dartec at Cranfield University on the 2nd of March. Between 11 in the morning and 5 p.m. And we have the CAA coming along to join us. We have Kevin Woolsey, Mark Worry and Callum Holland coming along to discuss and engage and have sensible conversations with our members and the wider drone industry. Do please join us. We'd be delighted to see you, clearly, obviously as members, but if not, you're very welcome to attend as guests virtually. Thank you very much again, James and Jonathan, and I will get this posted to the website this afternoon. Thanks very much then, everyone. Take care and bye-bye. Have a good afternoon.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.